In our discussion about comparing groups on a quantitative response variable, we have finally come to the time when we're going to talk about inference. Up until now, most of our discussion has focused on determining what is happening within our sample, although when we talked about mean squares, we started to wander into the area of inference because we started talking about how sampling from the population could influence those mean squares, and how by looking at the mean squares for the groups and how it compares to the mean square residual, it hints for us as to whether the group means are different in the population. As with any inferential procedure, we have to meet some conditions in order to have valid inference, so let's take a look at those. First, the groups must be independent of each other. So we're not going to have participants be in multiple groups. They need to be in one and only one group. Furthermore, from a research standpoint, if we are, say, implementing a treatment in one condition, we don't want any effects from that to bleed over into the other condition. If you're, for instance, implementing an educational intervention and you want one group to be a control group that doesn't have that intervention, you would want to make sure that individuals who are receiving the intervention are not taking that material and providing it for those who are not in the intervention. So groups need to be independent of each other. The units within groups need to be independent of each other. So when you choose your participants, if you can choose them at random, that helps with participation, or that helps with independence rather. It helps with independence. If you're choosing non-random, you need to make sure that you don't choose in a way that individuals you are choosing are somehow related to each other in terms of anything that might influence the response variable. Certainly, you don't want to take entire clusters of units like students in a class and consider them as independent of one another, especially if they're studying together, have the same teacher, and so forth. The residuals within the groups have the same variation. If they do not have the same variation, that can be problematic. Why can it be problematic? Well, because we're going to use the mean squares. And remember, I mentioned in the last video that the mean square residual, let's go ahead and take a look here at our plain risk data. This mean square residual is estimating a common variance among the groups. And if in fact they have different variances, then this cannot be an estimate of a variance. It's like you would need different estimates for different variances. There are procedures available that account for that. I'm not going to go into that at this point in this video series, but there are ways to deal with the possibility that you have different variations in different groups. And those are worth looking into, because I would think that especially in an experimental setting where you're implementing an intervention, you might expect that it would change the variation in a group. In the meantime, what do we do if the groups do not have the same variation? Well, we consider our estimates to be rather rough and crude estimates. We're still going to learn something, but we're going to have to be careful about how we interpret such things as p-values, since they rely on us having the same variation in each of the conditions. So this residual within the groups have the same variation. That's often called homogeneity of variance. Have you ever had to deal with that before? Well, if you've been with me and watching my videos, yes, you have, because when we talked about multiple linear regression, I brought up the condition of homoscedasticity. And what did that mean? That meant that no matter what the value of your explanatory variable, that the residuals at that value of the explanatory variable should have the same variation as residuals at other levels of the explanatory variable. We called that homoscedasticity. Think about it. It's the same thing here. Even though we often call it homogeneity of variance when we have a categorical explanatory variable, what do we have? We have the different levels of the explanatory variable, and we're basically saying, hey, if you're at that level of the explanatory variable, you expect to see the same variation as another level of the explanatory variable. That's homoscedasticity. Same thing. So homogeneity of variance is really just a synonym for homoscedasticity, but we tend to say homogeneity of variance when we have a categorical explanatory variable. Now let's go ahead and check for that. The first two conditions, groups are independent of each other and units within groups are independent of each other. We're not going to check those statistically. I'm going to suggest that you include that in your design elements in your study. But let's go ahead and look for residuals having the same within group variation. So I need a code chunk here, and I'm going to put in some functions, and this should look familiar to you. What am I doing? I'm plotting fitted values and residuals. Fitted on the x-axis, residuals on the y-axis. And you've seen a plot like that before. And what are we looking for? We're looking for similar variation in all three of those conditions. And right now, it looks like they're not perfectly similar, but it looks like they are a lot similar. That is, there's going to be a little bit of difference in variation in those, but this is not bad at all. If we want to take it a step further, we can look not only graphically, but descriptively. Let's go ahead and create another code chunk here. And I've gone ahead and put in some code. So I'm now going to look at the residuals, but I'm going to look at it for the different categories that we have. And when we do that, here are the standard deviations for each of those. 30.5, about 25, and about 23. So you might say, well, how come I couldn't see that in the graph? That's because we're not seeing all the points and being able to assess all those points at once, because you can see, if you look closely, that there's some points that are overlapping down here. But this is not really that far off. Let's see, when we look at our mean square residual, if I take the square root of that, the mean square residual was 66.3, and the square root is 25.8. So I'm basically estimating 25.8, where here I have 30.5, here I have 25, here I have a little bit under. So this one here is a little bit more, a little bit over the others, but these two, egalitarian and hierarchicalist, are close. So what I would say is that I don't have perfect homoscedasticity. I'm never going to, because of sampling variation, but it's not too bad. It really is not too bad to be off by an estimate of say 26, and I'm off about 4 here and 2 here and 3 here. So that's not too very bad. What is the consequence of being off? Again, we're using this mean square residual as a common mean square residual, and note it's in the denominator of our ratio. When we take the ratio, if this is a little bit off, then that's going to throw off our ratio a little bit. But as long as relatively it's not far off, and notice right now I have 4146 up here. So let's say that this should have been a better estimate, would have been something like 680 or 630. It wouldn't have changed that F value too much. So I'm not too very worried about it. Okay, the other condition that we had here is that the sampling distribution of means are normal distributions. The residuals should be normally distributed. And if we don't have a large enough sample size, the central limit theorem can be invoked if the residuals are not really normally distributed. So the central limit theorem can't help us with not having homogeneity of variance, but it can help us with if we don't have normal distributions. So let's go ahead and see how to check for that. And you've seen this before. We're going to establish a QQ plot. So I've created a standardized residual. I'm doing a QQ norm and putting a line through it. And it looks like we've got skew in our data. This would be right skew because we have the lower tail above our theoretical line and the upper tail above our theoretical line. So we have right skewed data. In this case, we have 225 observations, and so I'm really not very worried about this because by the central limit theorem, I expect the sampling distribution of our means, the sampling distribution of our F statistic to still be close to the probability distribution. In the case of means, it's a normal. In case of the F statistic, it's an F distribution. So if I had not had a big sample size, then I would be concerned that the skew is going to alter the probability to be quite a bit different than what I had anticipated, but that's not the case here. So up here, fairly reasonable homogeneity of variance. The other thing I'll say about the homogeneity of variance, if I'm a little bit off, is that once we get into our specific comparisons, remember right now that we're only dealing with a broad research question. Once we get into specific comparisons, we're actually going to be able to account for this. If you recall, when we talked about multiple regression with quantitative variables, I talked about the problem being not having homoscedasticity is that you were using a common standard error that was throwing off some of your coefficients, that your interpretations would not be quite correct with those coefficients because of the way that you're interpreting the standard error of those coefficients. But when we get into comparisons, specific comparisons of means, as we're going to do, we're actually going to account for the possibility that we could have unequal variances. So I'm not too concerned about that at this point. So even though I've got skew, I got big enough sample size, even though I had standard deviations down here that were different, they're not different enough to concern me. They don't affect my F ratio much. Plus, I'm at some point going to get into specific comparisons where I can handle it even if there are differences here. Okay, so we will end this video now, and having talked about conditions for valid inference, and in the next video, we'll actually make those inferences.